to present my work, which was about spatial and temporal correlation of heterogeneous infrastructure data, as Peter already introduced. And to give you a short idea why we do this, or what's our motivation, is that we think that the maintenance and the repair of road infrastructure can highly benefit from a good information base that supports some decisions. And in this information base, it would be good that if infrastructure would be represented as a system consisting of various subsystems and also taking into account the dependencies and the interactions between the different subsystems. And this would, at the end, allow us to apply statistical methods to assess some correlations between the different subsystems of road infrastructure. And to illustrate this a bit further, we can look into an example use case where we have a bridge and a road. And of course, they kind of influence each other because roads lead over bridges. And yeah, we have conditioned data to both subsystems. The bridges are inspected in certain intervals, and on roads we have, for example, some traffic countings that happen there. And from the bridge inspections, we have some bridge condition data, and from the traffic counting, and we have some traffic data that happened on the road. And we have this data not only in one point in time, we have this data is collected at several points of time. So at the end, we have some condition development data on the one side, and we have some traffic development data on the other side. And now it would be interesting to see if there's a correlation between this different condition data, or if there's a correlation between these different data sources, and if this correlation can be described through a regression function, which could be found by regression analysis. The problem with the data that we have right now, or with the systems that are currently in use, is that we have a siloed data storage due to current practices. Furthermore, we have a big heterogeneity between the different data models that are involved, and we have also the neglection of relations between the different subsystems in the systems that are currently in use. And this leads to the problem that we are not able to perform an automated association of data sets to each other, which would be the basis for a correlation analysis in the next step. So the problem at the moment is that we need this automated association of data sets based on their relations to enable the correlation analysis. And this automated association based on the different relations between the data is the point where we focus on in our paper. And the general idea is that we have the legacy data where we start from, and then to enable the comprehensive evaluation of the data, we create some graph representations of the legacy data to evaluate them comprehensively. And then we add some further graphs where we describe the relations between the different subsystems or the different legacy data graphs. And here we consider spatial relations and temporal relations. And then we look at this all together, combine the different subsystem graphs, and this forms then our knowledge graph representation of road infrastructure. And if we then would like to evaluate some relations between the different subsystems, we, following the approach of pattern matching, meaning that we define the relations that we are looking for as a pattern graph, and then we're looking for this pattern graph in our overall subsystem or in our overall road infrastructure graph. And as our overall road infrastructure graph is distributed in multiple subgraphs, this leads to a process where we first look into the spatial relations. So we divide our pattern graph into the part where we look for the spatial relations, and then the other pattern describes the temporal relations. And at the end, we have the matches that gives us then the data sets that possess a certain relation. So from these matches, we can then extract the data that we would like to find because of the relation that they have. We can plot them against each other and are then capable of performing a correlation analysis. To come a bit down from this high-level approach, we can go back into our example where we have the road and the bridge. The road has with the road assigned is some traffic counting point with some traffic counting data. And on the other side, we have the bridge, where we have some bridge inspection data or some condition grades for the bridge. And first, the spatial relation between the assets reflect the functional dependencies, meaning that from the spatial relation, we know which counting point counts traffic that leads over which bridge. This is nice so far, but we furthermore need the temporal relations between the data, because we also want to, or we are mostly interested in the cause and effect dependencies between the data, so we need to assign a certain traffic counting to a certain bridge condition data. That's why we need the temporal relations, and if we go a step further, we use some existing approaches for the spatial relations. We worked on this earlier, and now we focus on the temporal relations in this paper. If it comes to the association of these data sets based on their temporal relations, I mean, we showcase it here with some, as it would look very simple, but indeed we have the problem that we have, of course, an independent condition recording if it comes to roads and bridges or in general different subsystems. So we have the problem that we have some heterogeneous in the time references, which are due to the different applied methods for the condition recording. So we have different frequencies, for example. Furthermore, we have differences in interval length, and also we have irregular intervals sometimes, and furthermore, we also have sometimes different intervals how long a certain condition value is valid. And this should then, but this we want to like to use to enable something like a regression analysis, where we have usually some independent input variables, we have some output variables, and in between we look for a regression function. In our case, we have the traffic counting data on the one side, we have the bridge condition data on the other side. We want to plot them against each other to, at the end, try to define a regression or a function that describes the relation between them. And if it comes to dealing with such heterogeneous time references and enabling correlation or regression analysis, there is already an approach that could be used, and it's proposed by Alan, and it's called Alan's interval algebra, and he basically proposes the use of relative temporal relations for assigning heterogeneous time reference data to each other. And we use this for the creation of our graph, where we describe the temporal relations. In our graph, we explicitly model the relation between the data sets and refer the data sets on the timeline. And then we use again our pattern matching, where we then define every relation that is possible, defined by Alan by a certain pattern, and then look in our graphs for occurrences of this pattern to extract the elements or the data sets that possess a certain temporal relation. To go again in our example to make this a bit more clear what this means, we again have the legacy data from the roads or the traffic counting points and the bridges. And first of all, we have to create the graph representation of the legacy data. In case of the traffic data, it looks like that we have the counting point in the middle and some traffic data that is assigned to the counting point. These are the blue nodes. Then we have the structure data on the other side, and we have the representation of the structure. This is the yellow node in the middle, and we have the inspection data or the condition grades that are assigned to each structure. Then, of course, we have to perform the evaluation of the spatial dependencies to assign to find the asset pairs that have a spatial relation that we are interested in. We do this using existing approaches, and the result are asset pairs where we have structures assigned to counting points or traffic counting points. And from this, we can then start for each pair that we found to assess the temporal relations that they possess. And this we do by creating the graph to evaluate the temporal relations. For each pair, we have such a subgraph as depicted here. We have the time reference element and the different data sets that are represented as nodes, and each assigned to, each with the timestamp that represents the relation to the time axis. And then we go on the next step. So here's again illustrated what's in each subgraph for each pair. We have the time reference element, and we have the different data sources with the relation to the reference element. Then for extracting the data sets in a certain temporal relation, we have to define the corresponding pattern graph, which here describes the relation of traffic data, which was recorded right before the last bridge condition data. And using for occurrence of this specific pattern, we can then associate some traffic data with some bridge condition data. So at the end, we have the problem that we still have some traffic data that is not assigned to a certain bridge data. So then we play a bit around and use the opportunity to also see some bridge data as an interval. So now we consider bridge data as valid as long as a new bridge data is recorded. have to define a new pattern graph, of course, and are then able to associate each data set to each other. If we are now coming to results and conclusion, we use knowledge graphs for representing road infrastructure as a system with spatial and temporal correlations. We use Allen's interval algebra for handling heterogeneous time references, and the association of data sets is performed based on pattern matching. And this forms then the basis for correlation analysis, which leads to the future work, which is, of course, conducting such a regression analysis. If it comes to limitation, we neglected the time dependence of spatial relations at the moment, and also we build on comparable interval sizes, because otherwise our approach wouldn't make sense to assign some data points. And then we have some acknowledgements, and I'm open for questions.